Without a rate limiter, only one user is enough to take your entire API down. Hello, I'm Rahul and I'm a backend engineer. I have shipped rate limiters to production. Today, I'm going to show you an algorithm that you need to know, and most importantly, which one to use and why. 5 algorithms, 1 winner, and 0 fluff. Let's go. Here is what we're going to cover. We'll start with the problem, because if you don't understand why rate limiting exists, the algorithm won't make sense. Then we go through all 5 algorithms. One by one, I'll show you each one live with an animation. So you can actually see how it works. And at the end, I'll tell you exactly which one to use in a real system and how to implement it with Redis in about 10 lines of Python. If you are preparing for system design interviews, stick around. This is one of the most commonly asked topics and most people get it wrong. Okay, so why do we need rate limiting? Imagine you have built an API. It's live, people are using it. Now imagine one person or a bot starts sending thousands of requests per second. What happens? Your server starts struggling. Response times goes up. Then your real user, the paying ones, start seeing errors. And if it gets bad enough, your server crashes entirely. That's called a denial of service. Now, here's the thing. A rate limiter adds less than 1 milliseconds of overhead and it prevents all of this. That's why every production API has one. So what is a rate limiter? Simple definition. It's a component that sits in front of your API and says, this user has already made X request in the last minute. I'm going to block the rest. Look at the flow. User come in, they hit the rate limiter first. If they are within the limit, the request goes through your server and database. If they're over the limit, they get 429 response. That sends for too many requests and the response bounces back immediately before it ever touches your server. For reason, this matters. High availability. One user can't hog all your capacity. Abuse protection, bots, scrapers, DDoS attacks all handle. Scalability, your database doesn't get harmed at traffic peaks. Cost control, cloud compute isn't cheap. And runway traffic means runway bills. Alright, now let's talk about how it actually works under the hood. 5 algorithms, starting with the most popular one. This is called the token bucket algorithm. Here's the mental model. Imagine a bucket. That bucket can hold, say, 10 tokens. Every second, 2 tokens automatically refill into the bucket. Now, when a request comes in, it reaches into the bucket and takes 1 token. If there is a token available, the request goes through the green light. If the bucket is empty, the request gets rejected. 429. Now, I want to show you 2 more algorithms back to back, because together they teach you something really important. First is leaky bucket. Think of a bucket with a hole in the bottom. Request come in and fill the bucket up. But the bucket drips at a constant rate, always the same speed, no matter what. If request comes in slower than the drip, no problem. If they comes in way faster, the bucket fills up and overflows. That request gets dropped. Let me show you. A burst doesn't burst through. It gets queued and processed slowly. This is great for payment systems. You do not want a 50 payment requests hitting your bank integration at the same time. You want them to trickle through steadily. Now here, if you send multiple requests, as you can see here, the requests are getting dropped. And if we try to put single request at a time, it is getting processed or getting queued. But if you try to put maybe 6 requests at a time, you can directly see all requests are getting dropped. But most of them, based on our bucket size, will get queued as here. Right? Now comes the next request, which is fixed window counter. This one is dead simple. Count how many requests happens per minute. At 60 seconds, reset the counter to 0. Repeat. If the counter goes over, your limit reject. Super easy to implement. 1 integer, that's it. But there's a problem, and it's a bigger one. Look at this. Now here, if you see, if I send request here one by one, it will be allowed based on this window size, and it gets reset when the timer get completed to 5 seconds. right? Now, what happens if we send 10 requests exactly at this point? So let's try that. And here I clicked. Now it says boundary attack detected. So what happens here is 5 requests were sent when it was about to end, and 5 requests were sent exactly of start of the window. So because of that, what happens is we are blocked for 2 minutes. This is the problem with fixed window counter, and this is called boundary attack. And that's why fixed window is only safe for internal services where you are not too worried about precise enforcement. Now, let's move to the next one, sliding window log. The natural fix to the boundary problem. Don't use fixed windows, use a rolling window. That's sliding window log. Instead of how many requests happened this minute, you ask how many happened in the last 60 seconds from right now. And to answer that exactly, you store the timestamp of every single request. New request comes in, scan the log, count how many timestamps are within the last 60 seconds under the rate limit. Allow it. Append the timestamp over the limit 429. Let's see this with an example. Watch the dots on the timeline. Each one is stored timestamp. Old ones slide off the left edge as the time passes. The window is always the last 5 seconds. No reset, no boundary attack, no exploit, perfectly accurate. But watch the memory bar at every single timestamp here. Now, if we send more and more requests, it says allowed. But what happens when we click more than the allowed request? Let's send it. Now, at this go, we have sent some 8 requests and only 5 were allowed, right? And all others were rejected. At 10,000 requests per second, that's 10,000 timestamps per second per user. With millions of users, you are storing hundreds of millions of timestamp in memory. That is not realistic. At scale, sliding window log is the right call for high security, low traffic endpoints, login password reset, two-factor authentication, places where you need perfect accuracy and volume is naturally low. For a public API serving millions of users, you need something better. Now, here is our next algorithm, the sliding window counter. And this is the one same rolling window idea, but instead of storing every timestamp, you keep just 2 numbers. Count from the previous window, count from the current window. Then a weighted formula gives you the estimate. Previous counter into overlap ratio plus current count if 60% of the previous window is still in scope. You take 60% of that count. Watch the formula. Let's understand this with the animation. Watch the formula update live as request comes in. Is it perfectly accurate? No. It's an estimate about 98%, but it's accurate enough for rate limiting, and it only needs 2 integer per user. O of 1 memory, no timestamp, no boundary attack, no burst problem. This is what Stripe runs. When the interviewer asks, which algorithm would you use? This is your answer. Now let's compare all 5 side by side. Token bucket, burst allowed, O of 1 memory, default for most public APIs. Leaky bucket, no burst, smooth output, payments, billing, downstream protection, fixed window, easiest to build, has the boundary bug, and is only used for internal and non-critical systems. Then comes the sliding window, perfect accuracy, O of n memory, high security, low traffic endpoints only. Sliding window counter, bursts allowed, O of 1, 98% accurate, production winner. Most people in interviews list all 5 and shrug. Don't do that. Make a decision, say I'd go with sliding window counter. Here's why it fits our requirement. That's what a senior engineer sounds like. Now here's the part most tutorials skip, and this is where it gets real. Everything works great on a single server. In production, you have 10 servers, maybe 50, each server with its own counter. User hits server 1, 5 requests allowed. Same user hits server 2, 5 requests allowed. Total 10, twice the limit. Completely bypassed. So to fix this, centralize the counter in Redis. Redis INCR increments a counter automatically. Automatically means no race condition. 10 server hit it at the same time. Milliseconds counter is always correct. Key, increment and expiry, 10 lines of code. That's production rate limiting. One more thing, product decision, not technical. Redis goes down. What happens? Fail open, requests go through during the outage. Brief abuse, window user happy, fail closed, request blocked, no abuse, but users blocked too. Most APIs fail open, which means they do allow the extra users. Payment APIs, security critical endpoints fail closed. So for certain APIs, we are definitely going to close endpoints. Let's move to the last part of this. So what are the key takeaways? Token bucket is your default, bursts allowed, O of 1 and simple. Second, leaky bucket for constant smooth output, payments and billing systems. Third is fixed window for internal and low risk services, never where precise enforcement matters. Fourth, sliding window log for perfect accuracy at low volume, login auth, password reset, not for high traffic APIs. And the fifth one is sliding window counter. This is the production pick, accurate, O of 1 memory, no boundary issues, Stripe, Cloudflare, GitHub, and more. And in distributed systems, none of this works without Redis. Increment plus expire, automatic, no race condition, system design interview, starts with requirements, pick sliding window counter, explain why, mention Redis for distributed. That's the answer that gets you the job. Next video, comment down below HLD, and if I hit 50 comments, I'm going to create a new video on rate limiter system design, full with Redis cluster, multi-region, everything. Drop a like if this helped. See you in the next one. Thank you.